The next topic that we'll be talking about today is expansion of solid, liquid, and gases and how we can use it for our own advantage. So, before getting into the applications of expansion of solid or liquids, let's just talk about how it actually works and why materials expand or contract in certain environments. So, in general, when matter is heated, it expands, and when cooled, it contracts. If the changes are resisted, large forces are created, which are sometimes useful, but at other times they are not as useful. According to the kinetic theory, the molecules of solid and liquids they are always in constant vibration or constant motion, and when they're heated, they vibrate faster and force each other to be a little further apart, and hence we experience or we observe expansion. Expansion results, and this is greater for liquids, obviously, because they have less intermolecular forces and more intermolecular spaces already. Gases even expand more. So, expansion is slight for solids, and then it is a bit observable for liquids, and for gases, they expand, 2x folds, or they can really expand to huge lengths. So the linear expansion of solid it's small, and for the effect to be noticed, the solid must be long or the temperature change must be large. So for in order for the expansion to be actually noticeable, it is very important that the solid that we are observing is long, has larger length, and also if the temperature change is really huge. So I'm gonna explain it using some drawings. First part is that we have solid. So let's just say this is a solid block, or we can just start with gases because that just make less particles inside. So these are just two, three particles of gases inside this container. Now, obviously, if I and if it's not a container, if it's not closed, let's just say there isn't this lid on top of it, and there are just these molecules inside this container. So what basically happens is that if I erase this, it's gonna erase completely, but I'll just draw it. Yeah, so that's how. Yeah. Okay, so what happens is basically that if you give it some heat or you put it on stove or whatever, obviously the gas expands, and since they already have very weak intermolecular forces and they are not really um, attracting any other particles too, as stated by kinetic molecular theory, what happens is that they move further apart and we say that the gas expanded. Now, it's really easy to understand this in terms of gases, but when it comes to, let's just say, liquid, and there's this liquid that is inside this container, and they have, some noticeable molecular forces that are binding them together. I mean, it's not really the best um, depiction of a liquid molecule structure, but we're just gonna go with this. So what happens is that when we give it some heat, what happens is that these the molecules they move further apart and the liquid expands. Now this should be done in some certain specific environment, because there are different effects of heat on a state of matter. It can also get into the changing or transition of state of matter, but if let's just say we are ignoring all of that, and if it's in certain circumstances where it can only be expanded, so it's pretty easy to just imagine that these molecules will move further apart and the liquid will expand. Similar is the case with solids, but what happens is that since solids are really tightly packed together and they have very small intermolecular spaces, so it's really difficult to observe that expansion or that negligible uh, expansion. So what we are going to do is that in order to observe it, it's really important. Like the places where you can observe solid expansion in real life is one of the biggest example is that of cable wires or the wires that are hanging down the pylons. So what happens is that these wires are they're made a little loose than what how they're needed, just because in summers sorry, in winters they tend to contract, and let's just say if they were already a bit tight or already of that certain length, then there is some chance of them collapsing or them contracting too much, um, that they eventually break or form a crack or something. So this allowance or this slack is already left there to avoid that. So that's an example of solid. And even in this case, you can see that obviously we're talking about wires. They are long, and so that's basically causing us to notice this expansion change. Okay, so similarly, this is another example, which is basically just we have some diagrams over here that this ring-like shape is basically called a washer, and this rod is a rod, or I mean, you can call it anything. So what happens is that initially, when they're made or they're machined, these parts are formed. They're not. You can't really assemble them together. That's because the allowance between the diameter of this rod and the diameter of this inner circle or inner hole, it's not a lot, and it's not probably the diameter of the washer is smaller than that of um, the rod. So in order to what happens is that this difference or this tolerance is basically kept like that deliberately, because we want it to be like that, because if they were of the equal size, then if you can fit them together, it's also possible that you can open them easily. So they're built this way. What happens is that we just to push them in or just to assemble them together, we either contract the rod so that its length is just very minutely decreased, or we increase or expand. In order for the washer to expand, we heat it up for some time and then uh, you know push them together or assemble them. So once they're assembled and when they come back to room temperature, they're really taut and really assembled together really well. So that's how these metal parts are fitted together without welding, and it's called basically shrink fitting. These diagrams show how it works. This is first, and this is second. That we, in this case, we basically shrank the rod and we put it in, we put it in some fridge or something, and it got really minutely thinner than how it was before, and now you're able to like push it in. But when it comes back to the room temperature, the normal temperature, it is probably fitted in properly fitted in. So that's how basically we make use of this expansion and contraction. Okay, so now we do, we are making use of all these applications of expansion or contraction in our daily life and in engineering work, especially. But there are also times when we really don't need these expansion. What happens is that So what happens is that you need to, take these precautions to avoid expansion. And for them, what happens is that gaps. The biggest example is that of the gaps that are left on the railway tracks. They used to be left between the lengths of the railway lines. So what happens is that this is a railway track. You know, Now instead of making one huge rod or uh, you know one unit length of this track, they're made in these laps or these pieces with these gaps inside, this gap or this gap. The use of this gap is basically it as a precaution against expansion, that provided these railway tracks expand in scorching heat, where they'll fill this gap instead of going out of bounds, or instead of causing some problem, or instead of causing some bumps or other deformations on the track. uh, they just simply have this slack over here, so they're gonna fill it instead of causing some other deformation. So it's really smart how you can make use of it and use it as a precaution against expansion. They caused a familiar clickety click sound as the train passed over them. Since obviously there, it's not one continuous length of railway track, and they have these um, gaps on the railway tracks. So when the train passes over it, they make this, whatever it's called, clickety click sound as the train passes. These days, rails were welded into the length of about 1 kilometer and are held by concrete sleepers that can withstand large forces without buckling. Also, at the joints, the ends are tapered and they are overlapped. So, on these joints, the ends they're basically tapered. They're not just left all faceted. They are tapered so that when they can overlap like this, right? Uh, I mean, this is also an example. This is an example of heating pipes, but we can also use it as railway tracks because that example is also similar. So they're tapered like this, right? So instead of being all faceted and straight normal to each other, because you never know, it's not certain that in which direction is expansion going to happen. So they're tapered like this, so they can really fit in this gap in the most surface area way. So in certain heating pipes, expansion joints are used to join lengths of pipes. These allow the copper pipes to expand in the length inside the joints when carrying very hot water. So this is they're talking about basically this in this case too, it's not tapered, but it's like a complementary shape, like a jigsaw puzzle or something. That when they are heated too much, or when the water that runs through these pipes is really of high temperature, so they have this room for expansion. So this room for expansion is left on the expansion joints. This joint is basically this network of metal body that is made over here. Okay, now very important application of expansion is basically bimetallic strips. What happens is that there are different expansivities of different materials. Some expand to a greater extent than other materials, and we just make use of that certain property, that the expansivity of different materials is different, and build up this thing that is called a bimetallic strip. So basically, a bimetallic strip, uh, it has equal lengths of two different materials, such as copper and iron. They're riveted together. So as you can see here in this diagram too, that there are two rods or two strips of metals, and they are riveted together. So they cannot move separately. They form a bimetallic strip. So basically these two strips, they cannot expand, or they cannot make a certain movement uh, separately, since they're riveted together. So now they now act as one body. So when they're heated certain side, or what happens is that one metal, it expands more than the other metal. In this case, copper expands more than iron, and to allow this strip to basically experience that, the the copper curves more than iron, and that causes the strip to bend like that. And we can really make use of this property of bending uh, on certain temperatures in different applications, or in different areas. Let's just say one of the biggest example is that of fire alarms. Fire alarms work on bimetallic strips, and we are going to look into that. If they had expanded equally, the strips would have stayed straight. Bimetallic strips have many uses. So the reason why we have two different metals of different expansivities is basically because, let's just say we had two strips of um, of different of same expansivity, and we had just one strip of copper, then if it expanded, it would have expanded in just one certain direction, but and would have stayed straight. But in this case, this is copper that has been expanded, and then this is iron which has expanded but to very less extent than copper. So it basically, brings out this curvature or this curved bend shape. And we're going to talk about the applications of bimetallic strip now. So fire alarm. Fire alarm is the biggest is the biggest example of an application of bimetallic strips. Heat from the fire makes the bimetallic strip bend, and that completes the electrical circuit, so ringing the alarm bell. A bimetallic strip is also used in way to work the flashing direction indicator that when the temperature is of certain degree, the the angle to which the bimetallic strip bends is is a certain amount that it causes the circuit to complete and the alarm to ring, as you can see here. That this is a bimetallic strip. As we get heat from the fire, it will bend and the curvature will cause the bimetallic strip to get in contact with this plug and it will complete the circuit. This gap over here will be filled, right, like this. This will be filled, they'll start touching each other, and then the alarm rings. Another very huge example is that of thermostat, that a thermostat keeps the temperature of a room or an appliance constant. The figure is on the next page. Uses a bimetallic strip that is used in electrical heating circuit. Uh, when the iron reaches the required temperature of the strip, it bends down, breaks the circuit contact. So it's basically the opposite of that of fire alarm. That in fire alarm, the bend that was causing was upward, so it was basically closing the circuit and causing the fire alarm to go off and make some sound or the bell to ring, so that uh, the place where it is installed, we know that the fire has taken place and the bell is ringing. However, in thermostat, it is the opposite. That when we reach a certain temperature, the the appliance stops working. Let's just say if we had if we have that thermostat in a heater, or let's just say in an air conditioner, after a certain temperature, uh, the circuit breaks, and that is basically calibrated with the contraction or the bending of the bimetallic strip. So this is how it works. That heat surrounding, um, when it is heated, they join together, and then the heating element starts working. Or it could have been the opposite way, that if the um, bimetallic strip was attached upside down or in the other direction, then we could have used this, instead of heating element, we can use a cooling element or like an air conditioner in hot surrounding. So instead of bending like this, sorry, um, like upwards, sorry, because in this case it goes upwards. But let's just say if it was the opposite way, it would go like this and it will cause the circuit to break. So I mean, that's just basically intuitive. You can just use your imagination or creativity to make different applications out of it. Okay, this is linear expansivity, which basically makes use of the bimetallic strip and how that works. So engineer has to allow for the linear expansion of a bridge when designing it. The expansion can also be calculated if all the following are known: the length of the bridge, the range of temperature it experiences, the linear expansivity of the material to be used. So these are also some applications or some uses that are
that are basically made use of when we're engineering something or when we're drawing something, uh, modeling something. The linear expansivity alpha of a substance is the increase in length of 1 meter for 1 degrees rise in temperature. So that's basically linear expansivity. In order to like just explain it one more time, if we take 1 meter length of certain material and we observe that how much does it expand or how much does it increase in its length, because we're talking about linear expansivity, so we are not talking about volume, we're just talking about one dimensional expansion. So that is basically increase in length. So if we take a 1 meter rod of some metal, how much is it going to extend its length, or how much is there is going to be change in length when it is exposed to only 1 degree rise in temperature. So that is basically linear expansivity or F.